Hello and welcome to this wonderful webinar with Dr. Giuseppe Futia. Today we're going to be discussing leveraging synergies, LLMs, ontologies, and knowledge graphs in the biomedical domain for entity disambiguation. I dare you to say that 3 times very fast. But Dr. Giuseppe Futia has been a veteran of number of applications of knowledge engineering. He's worked in research, in academia, and in industry. So who better to give you a comprehensive view on these technologies through all these different ideas than Giuseppe? And with that, the mic is yours.
Thank you very much, Joaquin, for this kind introduction. And it is a pleasure for me to be here today to tell about this all this stuff that you mentioned, right, to the Swarm community. So to start this presentation, I would like to tell you that during this presentation, I will try to provide some perspectives, right, on the potential combination between all these technologies, so LLMs, ontologies, and knowledge graphs, try to leverage this combination for a specific task called named entity disambiguation, and try to apply this task in the biomedical domain. So this is the outline of the presentation. So I will try to answer to different questions. The first one is related to the potential opportunity that we have in the biomedical domain and what are the peculiarities of this domain for which we can exploit different AI perspectives, different AI technologies. Then I will go through a basic definition of named entity disambiguation. I will describe what is the traditional approach to perform named entity disambiguation before large language models. Then I will present some potential scenarios in which we can incorporate LLMs to improve traditional named entity disambiguation architectures. And then we will see what's next. What are the next opportunities in combining and leveraging the synergies between all these technologies. So as I told since the beginning, the biomedical domain is characterized by some specific peculiarities that can potentially enable these synergies. Because regarding the large language models, actually in the biomedical domain, we can treat a huge corpus of documents that provide textual content for different purposes, from research activity to policy support. In the biomedical domain, we also have several knowledge repositories that include different types of entities and relationships for diverse verticals. So, for instance, we have these knowledge ontologies that actually is a general purpose knowledge base, while we have more specific ontologies like the gene ontology and the human phenotype ontology, which describes, for instance, the relationship between specific phenotypic features and disease, right? At the same time, in this specific domain, we can condense all the information coming from this huge corpus of documents and these different knowledge repositories into knowledge graphs, which actually are complex graph representations that are able to integrate and incorporate information from heterogeneous sources, right? And you usually build these knowledge graphs for specific purposes and goals and application scenarios in the biomedical domain, including precision medicine, clinical data interpretation, disease model identification, and drug repurposing. So these are some peculiarities, right? These are specific characteristics of the biomedical domain that we can leverage in this specific context. To introduce the named entity disambiguation, I would like to share with you this simple example, which is a text extracted from a report of the European Center for Disease Prevention and Control. And you can see that in this portion of a text, I've highlighted the word Zika, right? So apparently in this report, the Zika terms occur 3 times, right? But the question is, all these occurrences represent the same entity of the real world. Well, if we analyze the surrounding context of these Zika terms, we can start to identify actually different potential entities at different expressions, right? Because the first one is the definition of the virus, right? While the second one and the third one actually represent some syndromes, some infections that are related to the Zika virus. In particular, the second mentioned here is a congenital form of the Zika virus infection. So these differences actually are clearly defined and encoded in biomedical knowledge base like the Unified Medical Language System, or UMLS, which is one of the most prominent meta-thesaurus in this domain. And as you can see that in UMLS, these 3 different entities are represented with distinct IDs, right? They are categorized in a different way, and they also are characterized by different definitions. But maybe the most interesting thing is that this difference is clear when we analyze the broader and the narrower concepts related to these specific entities, right? So for instance, in the case of the virus, you can see that the narrower concept is related to some specific proteins and genes that are related to the Zika virus and so on. While in the case of these syndromes and infections, we have completely different related contexts. So in the biomedical domain, these differences are particularly relevant, right, for detecting distinct entities. And you can easily start to guess, you understand that the name entity disambiguation and these differences that are encoded in specific knowledge base play a fundamental role, right? These are just some specific application scenarios, right? So for instance, in the case of the diagnosis, we have to clearly understand if we are talking about the broad Zika syndrome, or the specific syndrome of for pregnant women, right? Because in many cases, the treatment of the disease could be different, right? And this is related also to the impact of vaccines, right? So for instance, we have to clearly understand if we are talking about the congenital syndrome of the Zika infection, because we have to understand the impact of the vaccine, for instance, on the features. And regarding other applications like epidemiological surveillance, well, we should be able to distinguish in a fastest way if some reports just mention the Zika syndrome or mention the spread of the virus in a specific area or in a specific region, right? So this is why making this distinction is really important, especially in the biomedical domain. So how we can perform this named entity disambiguation? So how we can recognize and disambiguate entities that are available in medical text against an existing knowledge base or domain ontologies. This is a simple architecture, right, in which we identify the first step as a candidate selection. So basically, the input is represented by some annotated document with specific mentions, and then we have to understand which are the potential candidates, right, related to this mention. The Zika syndrome, the Zika virus, and the Zika congenital syndrome are clear examples, right, of potential candidates that can be associated with specific mentions. So when we detected these potential candidates that usually are encoded and defined in domain ontologies, which is actually it's the other input, right, of this specific component, then to each mention we have multiple candidates that are associated with, right? So the second main task and the second main phase is represented by the ranking. So basically, we can have multiple candidates, right, associated to a single mention, but we have to understand which is the best one, which is the target entity that is actually mentioned in the specific document. And the interesting thing is that the output of a named entity disambiguation pipeline could be used and could serve different purposes, right? For instance, we can use these results to, for instance, annotate some reports that we have in our repository, or we can create a knowledge graph, right? In this knowledge graph, we are able to condense information coming from the output of the named entity disambiguation pipeline, but at the same time, we can incorporate the domain ontology, right? So basically, the knowledge graph will include both the information. An interesting experiment that I did is try to understand how much large language model knows about UMLS, right? I started with a very trivial example in which I defined a very basic prompt, so zero-shot learning for the GPT 3.5 model, right? So I asked to the model to disambiguate biomedical entities in the provided text using the unified medical language system. And actually, I made this operation multiple times, right, in order to reach a good result. And as you can see, actually, the results looked good, right? He was able to identify, after some tests, different entities that are mentioned. But what I would like to focus on is the IDs, right? The model associated with these specific entities. As you can see, they are all the same, right? So these are the same number, but we have seen that in UMLS, actually, these entities are encoded in a different way. But the problem is that this number is also wrong, right? Because in the UMLS, it identifies this organic component that is used for as an antibiotic, right? So completely wrong response in terms of detected real entities from the text. So this is a good signal of the fact that the large language models cannot be used as they are, right, for these complex tasks. And this is related to their intrinsic limitations, right? Because these intrinsic limitations for the biomedical domain, for the named entities disambiguation task, becomes more stronger, right? In the sense that these limitations have a huge impact for this type of task. For instance, the case of the hallucination, the false or the misleading information can lead to an harmful impact when an high accuracy is required. There is the sensitivity to the perturbation that can play a crucial role, and it's a big issue, right? Because the biomedical domain is characterized by multifaceted and nuanced context. And there is this issue related to the concept drift, because in particular, the biomedical domain is a never-evolving context, right? Where new topics and new trends continuously emerge, and then the output of a large language model could be outdated based on my specific requirements. So how can we leverage the synergy? We have seen the limitation of LLMs, but let's see how we can potentially combine LLMs with the existing technologies to try to address these specific issues. So a very trivial example is actually what I have already shown you, right? So this is the pipeline, right? But if we decide to apply an end-to-end approach of fully based on LLMs, then we decided to leverage the compressed knowledge of LLMs for the full task, right? So zero-shot learning, but as we have seen in the example, this is not so effective, right? Due to the limitation of knowledge of large language models. So we can try to make an effort at the level of the single step, of the single phase, and try to see how we can combine the other ingredients. So we can start to use potentially LLMs for named entity recognition. So in this case, we have zero-shot learning. We can define and inject in the prompt some potential predefined named entities, because maybe we are interested in just pre-trained predefined named entities, or we can use the RAG approach, right, in which we incorporate further information to improve LLM's results. In this case, we can leverage the semantic network of UMLS. In this case, the box assertions means that we can use just the terminology, the vocabulary of UMLS, not the data by themselves. So this is an example of the sources that we can leverage. We can transform the description of the concept of disease, for instance, into a vector representation and store this information in the vector database. Or we can leverage the T-box assertions, so basically the high-level part of the ontology, into a graph database, right? And we can perform queries to this graph in order to expand the knowledge of the LLMs. We can work at the different level, at the level of the candidate selection. So in this case, we can potentially augment the knowledge of LLMs by leveraging trivial techniques like full text indices. We can potentially leverage the ontology, right? Exploiting, for instance, the neighbors related to a specific entity. So we can get not only the entity itself, but also its neighbors, right? So the nodes that are connected to this target entity in order to expand the information of the potential candidates. But at the same time, we can use embeddings that come from the graphs, right? Because ontologies are usually huge graphs, and we can perform graph-based technique in order to exploit this information as well. So the context change a bit, right? Because in the vector database, we can also store the information related to the specific candidates. In this case, this is just an example of description. And regarding the knowledge base, we can leverage, in our case, the context of congenital Zika syndrome. And this is particularly useful because, as you can see here, we cannot leverage the metadata, the textual metadata from UMLS, because it does not provide any definition about this specific disease. And we can potentially leverage graph embeddings. In order to make this approach effective of using graph embeddings, we can potentially flat the graph representation and process with the large language model. Or if we want to use the pure graph structure, we can potentially add a new neural layer in which we map the context, the textual content of a specific entity to the graph representation of these entities. This is a bit advanced, right? But this is something that can be potentially explored. And in the last phase, right, we can also implement and incorporate knowledge into LLMs for candidate ranking. So we can define, for instance, a measure of the relevance of the entity that can come from the textual corpus, so the number of occurrences, or the knowledge base itself. So in a knowledge base provided as a graph representation, we can leverage metrics or scores like PageRank in order to understand which is the most important nodes in the graph. And at the same time, we can combine the embeddings coming from the entity mention, the entity description in the knowledge base, and the ontology graph embeddings. And as you can see here, we can expand again our vector database, including information coming from the context, right? And this context is particularly interesting because the word microcephaly can be a word that can be used to detect further nodes that are not at one hop of distance to congenital syndrome that can enrich our context to get better results. So the idea is that this was our original architecture. We can empower at a different level this architecture with using large language models, but at the same time, when we create a knowledge graph at the end of this named entity disambiguation pipeline, we can reuse, right? We can reuse this condensed knowledge in order to perform the named entity disambiguation on new documents, for instance, or new reports, or on new or other type of contents. So the idea is that with knowledge graphs and ontologies and large language models, we can create a virtuous circle, right? And on the one side, this circle allow us to leverage large language model and graph models to build and enrich knowledge graphs. But on the other side, knowledge graphs can empower potentially large language model and ontology-based models to improve the named entity disambiguation. So this is the particular opportunity that we have when we try to combine all these technologies and all these approaches. So there are some other things that can be further explored, right? So for instance, in order to use these combined technologies in production, I would say, on the one hand, we have to increase the capacity of LLMs to formulate graph queries, right? Specifically for RAG applications. We can potentially inject OWL, which stands for Web Ontology Language, and other logic-based reasoning, because in many cases, we discuss about how large language models are capable to reason. But there are other artifacts, other type of technologies in which reasoning has been developed natively, right? So ontologies are built in order to perform reasoning. And this is something that we can further explore to identifying non-trivial connections between entities. There are some other approaches, right, that are very recent, like continual pre-training. So basically, try to rewarm our pre-trained model in order to readapt this model for a specific domain. And obviously, there is the fine-tuning, which is not so easy in this context because, as you have seen, we can potentially have millions of entities in a knowledge base for the named entity disambiguation. And at the same time, another interesting research direction is to encode large-scale knowledge graphs for LLMs. So we have to understand how to teach LLMs for reasoning using graph-structured information. So these are very recent trends that I think we can monitor, right, to understand the potential and new opportunities in using LLMs for production-ready tasks. And this is the end of my presentation. Thank you very much for your attention. I would like just to share that we can stay in touch, right, on LinkedIn and Medium. And this is a book, right, that I'm writing with other co-authors, Alessandro Negro, Blas Tacus, and Fabio Montagna, in which we treat all these topics, right, related to knowledge graphs, LLMs, and ontologies.
I'd also like to mention, Giuseppe, that you are developing some sort of educational offering around graph neural networks and knowledge graphs.
Yeah, exactly. I think that in the next months, I will release some contents, in particular on Medium and on YouTube. You have to decide if in English or in Italian about YouTube, but let's see. But yeah, in any case, I'm focusing on these activities, right, for the next months. So stay in touch, and I will provide all the updates and details on these channels.
I do want to say that if you have any questions, comments, concerns, or any observations that you'd like to share, feel free to put those in the comments below. And when we have more time in the near future, today, tomorrow, or within the week, we'll get to responding to those as they come along. I think Giuseppe painted a very clear picture that precision via named entity disambiguation and these multiple AI perspectives are fundamental ideas that we need to use to develop useful AI systems. If we can't distinguish entities amongst the varied context, what useful real world applications can we create? I don't think we can create many, particularly
Yeah,
in biomedical or pharmacology or legal or chemical. You could kill somebody or you could put somebody in jail. So very important to know what Zika you're referring to, how much of a dosage, what chemical compounds, and who is suing who. Those are very important concepts.
Yeah, definitely. And I believe that most of the effort, especially in the biomedical domain right now, is focused on developing chatbot, right? So basically developing machines that are able to interact with patients or with doctors. But the problem is that if we do not inject exact knowledge, right, on these chatbots, the risk is, I mean, huge, I would say. And in this way, we can build trust, right? Because if we do not inject this well-structured, predefined knowledge, we cannot build trust in these agents, right? Because due to the limitations that we discussed during this presentation. So I think that this layer, right, should be definitely considered, right, and combined in a fruitful way with obviously a machine that is able to chat and to interact with people.
Are you listening, hotel, tourism, and telecommunications utility companies? You can implement chatbots, but you hospitals and pharmacology companies get away from chatbots and really learn what all this knowledge means and map it so that we don't kill anybody. You can find
Definitely.
more creative ways of billing in the future, but let's save lives first.
Yeah, yeah, absolutely, absolutely.
All right. Have a good rest of your day, and yeah, we'll be in touch.
Thank you very much, Joaquin. Goodbye.